I have to share.
Participant, you will be there. Huh?
No, there's
Okay. Okay, I can see it here. Oh, yeah, I remember.
share.
Huh? I'll do.
Yes, sir.
Screen share. Good morning.
Good morning, sir.
Good
Sir,
morning.
they-
Good morning, sir.
Morning, sir.
So I hope I am audible and the screen is visible to all.
Yes, sir.
Yes, sir.
Both. Yes, sir. Okay, sir.
Okay. So just to recollect, in our previous session, we discussed about the scheduling aspect, then the different performance measures about the scheduling problem that we have discussed, and we also looked at the priority rules, or those we call it as dispatching rules, which are the first source of the rule by which the scheduling can be done. So we looked at the different priority rules regarding the scheduling, and then we looked at also the example that how we can do it in case of a single machine, or in case of the multi-machine situation, wherein we have the machines maybe arranged in a sequential way, which relates to a kind of a flow shop manufacturing or an assembly line kind of a situation. Today
Sir.
we will look at yes.
Sir, the sheet you shared all are password protected. So then how can we access these?
Which sheet you are talking?
Sir, last second week and third week also, sir. The Excel sheet is password protected, sir. And
I
we
think the
don't know the
data
password.
field are visible to all.
Yes, data field is visible, sir, but we cannot change
Data
anything.
field and the formula is also visible.
Yes, sir.
So that is what is expected, that based on that you have to practice it.
Sir, how can we
Because
practice, sir,
many times
if we cannot change?
so you can copy that data in some other sheet and you can use it. That copy option is not disabled, but just to avoid the any maybe the other use of it, that is password protected. Okay. And sometimes it happened that based on some working related with that particular sheet, if any wrong entry or anything that happens with the formula, and if the formula gets corrupted, so it may create a problem in the future. So to avoid that, the sheet is password protected, so that you may copy it, you can work with that, and based on that, you may manipulate that sheet. Okay, so that is what only the purpose. Okay, so just to protect that sheet from any manipulation, so that during working, if any delete button is being pressed or anything, if it happens with the formula, so
Sir,
that it
we
should not
have
corrupt your
we have
entire sheet.
learned, sir, we have learned the Excel in the first module. Then if it will
Mhm.
corrupt, then we can change it, sir. If password is password lock, then we how can we access and cannot practice this?
No, all the entire content you can copy it in some other sheet and you can work with that, na?
Okay, sir, we'll try.
Isn't it? That option is not disabled. So that if, because based on my previous experience, that once the sheet is formula, all those are set. And if by some means, if you are working on it, and if something happens with the formula, then it completely corrupt that sheet and then it's not useful in future. Or maybe some wrong
Sir,
interpretation it goes with that particular sheet.
sir, then again, if it happens, then again we can download the same sheet, sir,
Which one?
the which you uploaded.
So see, this is from the practice point of view, okay? When it's a practice, then you have to get involved in. Otherwise, what will happen? You will just look at it, the things will be readily available, and then you won't be able to extend the learning which is required in that particular.
Okay, sir.
Okay.
Sir,
But all the things that are accessible in that sheet, all the formulas you can see.
Yes, sir. See, we can see, sir.
You can copy those also. So you can make a copy of it. You may work with that, whatever changes, whatever practice that you want to do, so that if anything, again, it gets wrong, you may again visit to that sheet and you may work with that. I hope this
Okay,
is not
sir.
the problem. And this is what is expected as a kind of practice task that is expected from the participants. Okay, yes, Mr. Rangarajan.
Sir, for assignment, totally 3 questions are there. We need to answer any 2 or all 3 is must.
You may attempt any 2. If you do it all, then that is well and good from your point of view of learning.
Okay. Thank you.
So it's an open kind of an assignment wherein you may work with that example, or you may relate it with some situation, maybe related to your domain of work. And maybe based on that, you can practice the concept, so that it will give you an hands-on practice of applying the concept.
Assignment can be submitted as Excel sheet directly.
It's a kind of a report that you will have to submit based on the work that you will do in Excel, as well as you have to completely prepare a report and then submit it.
So you're expecting PPT, some kind of PPT or a Word file?
No, not PPT. It's a Word or PDF kind of a document.
Oh.
Okay. So it's not just working with the analytics. Your inference based on that, or what is your conclusion, or if any comment that you want to make it as a part of analysis, that you can include in the report.
Okay.
Okay. Is there any other issue? Okay, fine. So I hope all of you are practicing with that particular sheets which are shared with all of you. And as I mentioned, you can make a copy of it in some other sheet, and based on that you can practice the examples. Okay. So today we will look at the.
Yes, sir. After changing, it is happening, sir. After copying to the other sheet. It's working, sir.
That's what.
Yes, sir.
So that is the first thing expected in terms of practice. Because if everything is readily available, we feel that we don't have to do anything.
Yes, sir.
Okay. So it's an intentional act to force you to extend your learning. I hope, Faraz, you got the point.
Yes, sir. Thank you very much, sir.
Okay. Okay, so today we look at the job shop scheduling problem. So you can see that in any job shop, the flow in which the job will move from one machine to another machine, it will be a very haphazard or a zigzag kind of a situation, wherein the job can move from any of the machines. So we can see here in this example that the job 1, it will follow a sequence like it will go to machine 1 first, then machine 4, then machine 2, then machine 5, and then machine 6. Similarly, for job 2, the flow through which the job will flow across the machines will be different. So this is a kind of a very zigzag kind of a situation or a haphazard situation. So if you compare it, for example, we have discussed about the flow shop manufacturing or the mass manufacturing system or assembly line, wherein the job moves in a very sequential way. So there is a fixed sequence. So workstations are arranged, and based on that, the job moves from one machine to another machine. And in that case, the sequencing or the scheduling problem requires a different kinds of arrangement or a different kinds of approach. But in case of a job shop, you can see that there are 3 aspects which are essential from the job and machine point of view. The first one will be related with the processing time, then the operation, that is first operation on which machine it is performed, second operation on which machine it is performed, and then also the kind of machines that are arranged. So a job shop scheduling problem is a kind of a very complex problem wherein we have to look at that how the scheduling can be done. So today we look at how the job shop scheduling problem can be scheduled using the priority rules that we have discussed. So we will look at one priority rule, and maybe based on that, we can understand that to what extent the problem of a job shop scheduling, it gets complex, so that when the number of problem size or the number of jobs which are in the problem or for scheduling, when it increases or when the number of machines will increase, to what extent the problem becomes complex. And in that case, we need to have to use some algorithms based on which we can do the scheduling. So let's say here is an example. There are 4 jobs and there are 5 machines, okay? And so 4 jobs, 5 machines, and there are 3 operations that need to be performed. Okay, for example, here there are 3 operations. So the first operation, second operation, and third operation. So here it represents the operation. So for example, for job 1, and this represents the processing time. So for example, here job 1, the first operation will be performed on machine 2. So the number in the square bracket, here it represents the machine number. Okay, so for job 1, the first operation will be performed on machine 2, and it will take a processing time of 3 minutes, let's say in this case. Then the second operation for job 1 will be processed on machine 4, and it will take a processing time of 7 minutes. Similarly, the third operation for job 1 will be processed on machine 5, and it will take a processing time of 3. So in this way, for each job, you will have an operation number. That means first operation, second operation, third operation, because in case of a job shop, the job moves in a very haphazard manner. So depending on the processing requirement, depending on the operations that are performed on that job and which machine will perform that operation, and based on which machine the job is performed, it will involve its processing time. So in this case, similarly for job 2, the first operation will be performed on machine 1, and it will take a processing time of 6. For job 2, the second operation will be performed on machine 2. Its processing time is 3. And similarly, job 2, the third operation is performed on machine 5, and its processing time is 7. So in this way, the configuration of any job shop will involve the operation number, the machine number, the processing time, And based on that, we have to decide that in what sequence or what should be the schedule so that the required performance measure can be achieved. So from this itself, you can see that the complexity is very high because we have to look at 3 elements, and based on that, we have to decide the sequence in which the job will be flowing on the different machines. And then based on that, what will be the performance measure in terms of, let's say, the make span, or in some situation, it may be lateness. What do you mean by make span? Can you recollect what is make span?
Throughput time. Is it throughput time?
So make span is nothing but it's the time, because we are scheduling here multiple jobs on multiple machines. Okay. So make span, it represents the time at which the last job of the batch will move out of the particular machines. And what do you mean by lateness? It's nothing but the time at which the job is completed and the time is the due for that particular job. So if the job is completed beyond its due date, that's a late job. And if the job is completed earlier, then it's not a lateness, if we are not considering it in terms of the earliness penalty or earliness of that particular job is concerned. Okay. So
is it considering the lead time, sir?
Is
it considering the lead time or the
lead,
last machine time, last operation time?
So
as
in
3
this case,
operation has to be performed, so is it the lead time of combination of all 3 operations or the last operation
so
time?
let's say you have 4 jobs here. So each job will have a different sequence in terms of machines on which it will be processed. Okay.
Right.
So make span will represent whichever the job which will come out of the system last. So the time at which all the
it
jobs
depends on
will
the lead
complete
time.
its the time at which all the jobs will complete its processing, that time is called the make span time.
So means the time to complete the task by
The time to
performing all
complete
3
all the
operations.
jobs. Time to complete all the operations of all the jobs, that we call it as a make span.
Okay. Understood.
Okay, so let's look at this example, how we can do it. So let's apply the SPT rule. That means whenever we are looking at the job to process, the way in which the job will be decided, it will be based on the shortest processing time. So if the priority comes that out of the 2 or 3 jobs, which job we need to select, it will be selected based on the priority rule of SPT. So similarly, you may have the other priority rules by which you can make a schedule, and maybe based on that, you can compare the performance, and depending on that, you may select the particular schedule. For example, here, these are the 5 machines on which now we have to load the jobs. So out of these jobs, if we look at job number 2 and job number 4, job number 2 and job number 4, they are processed on machine 1. Okay. And job number 1 and job number 3, they are processed on machine 2. So if we want to load the job on machine 1, which jobs are available for first operation on machine 1? It is job 2 and job 4. So since we are using now SPT as the priority rule, so out of this job 2 is having a processing time of how much? It is 6. And job 4 is having a processing time of how much? It's 5. So which job will be given the priority? It is job number 4, because we are assigning the jobs based on the shortest priority rule. Okay. So now we will put the job number 4 in machine 1 for. So here we will have 2 notations. So we can say it is job number and operation number. So let's say we can say now here, out of these two jobs, job 2 and job 4, since job 4 is having a shortest processing time, we will load job 4 here for its first operation. So I can write it as 4-1. So 4-1, what here it indicates?
Fourth job, first operation.
Fourth job,
First operation.
fourth job, first operation. Okay, so 4-1 here it. Okay, so I will represent it like 4-1. That means first number is for the job number. So first number is for job number and second number is for operation number. So this job 4, its operation time is, its processing time is 5. So for next 5 minutes, job 4 will be loaded here. Okay. And job number 2, okay. And for first operation, what about the other jobs? So job 4 is done for first operation. Now job 2. So which will be the next job for first operation?
Second
Job
second
2,
job.
job
2-1.
And
Job
once the
2.
job 4 is finished, we can load job 2 for its first operation because it requires machine number 1. Okay. So we can see here 2-1. That means job 2 will be loaded for
6.
6 duration. So okay. So job 1, job 4 and job 2, its first operation is over. Now what about the first operation for other job? That is job number 1 and
3.
job 1 and job 3. So job 1 is performed on machine 2 and job 3 is performed on machine number 2 again. So now in this case also, which job will get the priority?
Job 1.
Its processing time is job 1's processing time is 3 and job 2's processing time is 7. So which job?
Job 1.
Job 1.
Job 1, because we are following the SPT rule. Okay. So in a situation, if you are using some other priority rule, it may be the longest processing time or it may be earliest due date. Depending on that, you will have to assign the priority to the job. So job number 1 will be assigned on machine 2. So it will be 1 for first operation and it will take how many minutes? 3 minutes. And then it will be job number 3 that will go for its first operation.
7 minutes.
Sir, how come it is 1-1?
Job 1 and operation 1. So notations here are first number, it represents the job number and second number, it represents the operation number.
Sir, Operation number, is this the sequence? What is the meaning of one? It is the name of the operation or it is the sequence?
Operation 1, first operation for job 1 has to be performed on machine 2.
But sir, job 1, there written 3 and 2. Here 2 is the
2 is the machine number. This is what is the convention. So in any job shop problem, you will have 3 things which will be involved. The first will be the machine number, job number, its operation number, and processing time, because each job will have a different requirement in terms of the machine, and each machine will require a different processing time for processing the job here. Okay. So don't take it as 11, it's 1, 1. First number, you take it as the job number, and second number as the operation number. Okay. So first job will be loaded on machine number 2, and it will take a processing time of 3. So once loaded here, for next 3 minutes, job 1 will be processed. Okay. And then job number 3 will be loaded on machine number 2, and it will take a processing time of 7. So for next 3 minutes, 7 minutes job.
Sir, here you are picking the shortest processing time, no sir. In the
If there
second
is
column, in the second column also we have 3, no sir, for the job 2 and operation 2.
See, unless the first operation is performed, you cannot perform the second. Operation number is also important. So operation number, it represents the machine on which it will go first. Okay, for example, let's say drilling and boring operation you want to perform. So the operation has to be drilling operation. So it will go to drilling machine first. It will have some processing on that, and then maybe it will go to a boring machine and maybe further requirement of the job.
Okay.
Okay. So maybe these colors will help you to discriminate between these. Okay, so first operation is over. Now what about the second operation? Now look at the second operation.
Machines 4, 2, 3 will be used.
So for second operation, job 1, it requires machine number 4. Job 2, it requires machine number 2. Job 3 requires machine number 4, and job 4, it requires machine number 3. So on machine 4, so here for second operation, M4, M2 and M3 are required. Okay. So based on the processing of the first operation, whichever job is free, that will be loaded. So let's look at machine number 4. So if you look at machine number 4, which job can be processed?
Job 3 should be processed.
Job 3 should be processed.
Job 1 and job 3. Job 1 and job 3. So job 1, because machine 4 is not yet loaded. So you can load the machine 4 now. Out of those, J1 and J3 are to be assigned on machine number 4. So job 1, what is the processing time?
7.
7
It is
minutes.
7. And what is the processing time of
3.
job 3?
3.
It
3.
is 3. And machine is free. You can see that no job is being loaded. So now which job you will load?
3.
Job
Job number
Job 1.
3.
3.
Which job you will load?
Job 3. Job
3,
3.
3, SPT rule.
So as per SPT rule, job 3 is due for loading. But if you look at the first operation between job 1 and job 3, job 3 is not yet free and job 1 is free. Which job is free?
Job 1.
So job 1 is finished here. Okay, that means job 1 is free. Job 1 is ready for loading. Job 3 is not yet loaded. So what you can do? We will load job 1 here for its second operation. So 1, 2. That means what?
Job number 1.
Job number 1
Operation
and
2. Operation 2.
operation 2. Okay, so even though as per SPT rule, you can load job, you have to load job number 3 for its second operation. Okay, so as per the SPT rule, job 3 has to be loaded. But then since job 3 is not yet ready, job 1 is ready for its second operation before job 3. And since machine is free, which job you will load first? You will load job number 1 for its second operation. So how much is the time? It will take
7
7
minutes.
So up to here, job number 1 will be loaded. Okay, so job 1 is done. Now, which will be the next job?
Job 3.
So can you load job 3 on machine 4?
Yes, sir.
Yes, but one minute we have to wait. Idle time will be 1 minute.
Job 3 is ready here. So we can load it here.
We can load it, sir. Straight.
Isn't it? The job 1 second operation, it takes 7 minutes. So this
Yes,
will be
we
free
can
by
load.
this time. Okay, so machine is free as well as the job is also free. Its processing is complete. So you can load here job number 3 for its second operation. And how much time it will take? How much time it will take? 3 minutes. Okay, so this is also done. Now, for second operation, so this machine is done, machine 2 and machine 3. So out of machine 2 and machine 3, which job? Machine 2, which job can be loaded? Job number 2, isn't it? And which job can be loaded on machine 3? It's job number 4. So how will you assign it? Which job you will load? So job 2 on machine 2. And job number 4 on job number 3 on. So this job and this job needs to be loaded. So which job you will select and on which machine?
So job 4 to be selected first.
So on machine 2, which job is to be loaded? Job number 2. Isn't it? So just look at the status of job 2.
It is still not completed.
So you can see here that the job number 2 first operation is finished here and it has to be loaded on machine this. So we cannot start it here. There will be a waiting time or the machine is not free, so idle time, and job 2 will be loaded for its second operation here. Okay, so how much time it will take? It will take 3. Okay, so job 2 is also over. What about job number 4? Now machine 2 is also done for second operation. Now machine 3. Which job is you can load?
Job number 4.
Job number 4. Okay, so where you will load it?
After
First
6th
operation
cell.
is finished
After
here.
5th cell.
So from this point you can load now job 4 for its second operation, and it will take 4. Okay, so job 4 second operation will perform here. So machine 3 is done.
So second operation for the job 3 should be in machine 3, not in machine 4. I think.
Second operation of job 3 is on machine 4.
But machine 3 is also there, no? For 4. The 3 only follows 4.
No, can you repeat the question?
If you see job 3, it is processed in machine 3 for 4 minutes. But this is the second operation. But we have gone straight away to machine 4 for second operation.
See, job 4 first operation is performed on machine 1. Okay. Then job first operation is performed on machine number 2. Is there anything wrong here?
No, I'm talking about job 3. For second operation of job 3, it has gone straight away to machine 4 instead of machine 3.
Job 4 second operation is on machine 3.
No, I'm talking about job 3, sir. Job 3, second operation should be in machine 3, not in machine 4, I think, for job 3.
Let me see. It may happen.
Job 3.
Job 3 second operation is on
Machine 3.
machine 4.
But next cell you can see is machine 3 is there.
Job 4, you're talking about job 4 or job 3?
Job 3.
Job 3.
Second operation.
First operation is on machine 1, machine 2.
Yeah.
So job 3's first operation is on machine number 2.
Correct.
Okay, so this we have done. It will take 7 minutes.
Okay.
And job 3's second operation is on
machine 3, it must be.
Machine 4.
Oh, based
The
on
number in the bracket, it represents the machine number. So you can see here job 3's second operation is on machine number 4.
the next cell is showing us 3, machine 3. A 4 bracket machine 3. The processing
This
time.
is job 4. Which job you are talking about?
If you take the row job 3, third cell, processing time 3, under processing time 3.
We
Yeah.
are not yet gone to the third operation. Okay, we are first looking at, because the operations will be performed first operation, second operation. So at this stage, we are looking at the second operation.
Okay, sir, but we
Okay.
have gone straight away to fourth operation. Instead of completing machine 3, we have gone straight away to fourth operation for job 3. Highlighted in green color.
There is no 4 operation here. Job 3 second operation is on machine number 4. Job 3, if you look at, its first operation is on operation 1 on which machine?
Rangarajan, but job 2 will
Machine
further
2.
be delayed if we do that, perform job 3 first instead of job, then job 2 will be further delayed because its second operation is still incomplete. I think your
So you
question is
have to
that.
look at, whenever you are looking at a job shop scheduling kind of a problem, you have to look at the job number, the machine number, the operation number also, and its processing time. And based on the processing time, you will see that whether the job is free, because the job can be only loaded when the job is also free and the machine is also free. Okay, so you have to assign the job to the machine based on whether the job is free or machine is free. If both are free, then only the job can be allocated to that particular machine. Okay, now will you look at the third operation?
Sir, I have a doubt. In
Uh-huh.
machine 2, okay,
Mhm.
after completing the 3-1, there is a 1 minute idle time. Okay, but if we go for go for machine 1, the second the first operation is finishing in 11th minute.
Correct. Job 2's first operation will get finished by 11th minute.
Okay, so
Okay.
sir, there is a 1 minute idle time also, na? So we are not considering this idle time here. It should be started from 13, na? Second job, machine number 2.
So by the time the job is free, so at this point the job is free. By this time, here you can see, by this time job is free here, and it can start its second operation from here.
Okay, sir. So means in this we have considered idle time also, and that machine finish time also.
See, you can load the job when the job is free as well as machine is free.
Okay.
So the second operation for job 2, it has to be done on machine 2. But since the machine job is free here, or the machine is free here, but job is not free. So that's why machine will have to stay idle, and after that only the job can be loaded.
Understand, sir. In this case, that both things are merged, idle time also and then machine. Okay. Understand.
So this red is indicating the idle time of the machine.
Understand.
Okay. So one simple thing you have to keep in mind, that whenever the job is free as well as machine is free, and the freeness of the job will depend on its processing time. That's why processing time, operation number are critical in case of a job shop scheduling problem. Okay, now can you look at the third operation? The third operation will be performed on machine 5, machine 3 and machine 4, M5, M3 and M4. So if you look at machine 5, which is not yet loaded, okay. So first job, third operation is performed on machine 5. Second jobs, so on machine 5, J1, which jobs will be due? J1 and J2.
J1 and
Out
J2.
of which job you can load?
J1 can be loaded first.
J1 and J2. So processing time is 3 and processing time is 7. So out of that, we will give priority based on SPT rule. So job 1. But then at second level, you have to look at which job is free. So since
Job
machine
1.
is free, so which job you can load now?
Job
Out
1.
of these two? Job 1 and job 2. So you can see that job 1 is free by this time. Job 1 is free at this time. And what about job 2? Job 2 will get free by this time.
14 minutes after.
So which job you can load here?
Job 1.
Job 1, because that is free. So job 1 for its third operation, and it will take how much time?
3 minutes.
3 minutes. So you will load job number. Okay. And then job number 2 for its third operation. So at what point you can load it? Once it is free.
15th minute.
So 2 you will load for its third operation here. And how much it will take? 7. Okay, so this is done and this is done. What about the remaining job, job 3 and job 4? So machine 5 is done here. Machine 3 and machine 4, which you can load. If you look at machine number 3, job 3 is to be loaded. So on machine 3, job 3 is to be loaded. So
4 minutes idle time.
So since the second operation of job it will be finished here. It will be loaded on machine number 3 from this point. So third job, third operation will be performed here. And how much time it will take? 4 minutes. Okay, so this is also done. And what about job number 4? Its third job will be performed on machine number 4. So job 4, at what time you can load it?
14th
The
minute.
job is free after its second operation at this point. So the job is free now, and it has to be loaded on machine number 4. So by what time you can load it? From here. So fourth job, third operation, it will start from here. It will take 5 minutes. Okay, so this is the way you will have to do it. So now you can see that all the jobs will be completed by what time? It will be completed at the 21th or 21 minute. Okay, and based on that, you may prepare a kind of a summary based on if you want to find the lateness for each job, for example. Now you can do the analysis which job so you can look at that. This is what is the idle time in the jobs for the machines. So all these are nothing but these are the idle times. Okay, so you can find the lateness for each job. Similarly, you can do the analysis in terms of which machine is idle. If you want to find the lateness for each job, for example, job 1, at what time it is completed? It's completed at 13th and its due date is 10. That means job 1 is late by 3 minutes. Job number 2, at what time it is complete? By 21st, and its the due date is 12, so it will be late by 9 minutes. Job number 3, it will be finished by 17th minute, and its due date is 9, so it will be late by 8 minutes. Similarly, you can find it for job number 4. So based on this particular SPT rule, you can see that this is what is the performance of this particular schedule, which is based on the SPT rule. So similarly, you can apply maybe some other rules, and maybe based on that, you may compare the performance. For example, in this case, you may compare the performance in terms of the EDD rule also. So the way we have done it based on the SPT rule, you can check the performance maybe in terms of the EDD rule, and based on that, which rule it gives you the better performance in terms of the objective that you want to fulfill, you may select that particular rule and you can use the schedule. So you can see here that for a simple problem like this, which is involving just 4 jobs, 5 machines and 3 operations, the complexity, it gets to this level. So when the number of jobs, number of machines, number of operations will increase, the complexity will get to very high. So that's why we have to use different algorithms, different techniques which are available to decide the schedule for the job shop scheduling problem. Okay, but I hope that the complexity and how we can do the scheduling based on these kind of priority rules in case of a job shop is clear based on this example. If any doubt related to this, you can ask. Okay, so you may try this example with the earliest due date criteria, maybe with the longest processing time criteria, and based on that, you can compare the performance of these 3 rules that you have used, and depending on which rule is giving or minimizing the lateness, that rule may be selected or it may be adopted for the scheduling purpose. So if any doubt related to this, you may ask.
Sir,
Otherwise,
yes, sir. So this method is available only manual method, sir?
No, of course, you can create a logic and it can be developed as a kind of a software.
Okay,
this is where how I have shown you that how we can do it, and then how we can represent it with a Gantt chart. Okay, so based on this logic, we may develop a software or a program. You may find one small software LEKIN. It's developed for the academic purpose, but then you may search on the Google also. Okay, and maybe up to 50 jobs it can give you a kind of a schedule.
This software is specific to only scheduling, sir?
For scheduling.
Schedule.
You can download it from the net. The academic version is available.
Okay.
And you may look at the schedule based on the different configurations of the production systems also in this. Okay, for single machine, for flow shop, and in that several algorithms are also being included. So for a smaller application, you may try this or you may use it also. But of course, this is for the academic purpose. They have their commercial version also, but then they have given an academic version which you can utilize it maybe for even up to 50 jobs configuration.
So the 3.3 version we need to use, correct, sir?
Which one?
Like in 3.3 we have to use it because introduces students to scheduling theory and to application.
Correct.
Okay,
Yes,
sir.
yes.
Thank you.
Okay, so this is about the complexity of the scheduling problem, and you can see that we have looked at the machine scheduling problem. But of course, when it gets to a workforce scheduling problem or any other format in which we need to come across preparing the schedule, there are different kinds of algorithms which are involved. So we can utilize those particular algorithms, and based on that, we may utilize it for the scheduling purpose. So I hope the concept and the complexity of the scheduling problem, I hope it is clear based on this particular discussion. And we'll stop for the scheduling discussion at this point of time, because we have to look at the other aspect of the course. So if you have any doubt maybe related to this, based on the practice that you will do, you may post it on either the Google Classroom or maybe through a mail, and we'll try to resolve it up. So we'll continue now our discussion for the other one of the important topic, which is related with the maintenance planning in case of manufacturing systems. Okay, so we can see that maintenance, which is one of the important aspect as a part of the manufacturing system or in any organization, and many of our productivity measures, they are based on how effectively maintenance is being planned and maintenance being implemented in any organization. Okay, so if we look at the different drivers of the business, for example, we say quality, quantity, cost, delivery, service. So to some extent, all these drivers are based on an important factor in the operations planning, that we call it as a maintenance. So maintenance is nothing but it will involve the combination of activities by which the equipment or the system will be kept, or it will be restored to a state in which it can perform its designated function. So all the activities by which, if any breakdown it occurs in the machine, or if there is some failure, and so by which you can restore that machine from a failed state to an operative state. So that particular activity, we call it as the maintenance. But if we look at the conventional thinking towards the maintenance, and if you look at the earlier days when the maintenance was a kind of a neglected activity in any manufacturing industry or in any operations. So unless there is a breakdown, the machine is not being attended. So the philosophy or the thinking was in terms of fix the thing when they break. So unless breakdown occurs, the machine were used continuously, and whenever any breakdown occurred, then only the machine is taken for maintenance, and then the machine is restored, and then further operations are performed. But when the things, when we say that we will fix the machine when it will break, but when the machine has failed, even though you have done some kind of a maintenance, that means the maintenance has also failed. So it's not the machine has failed, but in that situation, we can say that maintenance is also failed, because the job of the maintenance is to keep the machines continuously available for the required function. But that means if there are recurring failures that are occurring based on which the machine is not performing its function, that means we can say that the maintenance is also failed. And the maintenance job is to maintain it so that it should never break. So ideally, it is required that the effectiveness of the maintenance should be such that it should never break. But this is what is a kind of a idealistic, we can say, requirement or consideration. But realistically, it is not feasible, because due to continuous operation, the machine are going to fail because of the continuous operation of those particular machines. Okay, and we can see that in many manufacturing situations, the maintenance cost can be as large as 10 to 20% of the revenue. So this is some of the statistics which is based on the research, that whatever the revenue that is generated, maybe 10 to 20% of it may be lost because or will get consumed based on the maintenance activity. Because maintenance in earlier days, people used to call it as machines, but nowadays they are considered to be assets. And nowadays people talk in terms of the machine, in talks of the asset maintenance, asset performance or asset utilization, rather than in terms of the machine performance or the machine utilization. So if we look at the role of the maintenance, so we can see that in today's scenario where the thinking in terms of the maintenance of the machine is changing or has to be changed, because you can see that in today's markets where there is a lot of competition that exists, and in this competitive world to survive, the machines are becoming more and more complex, because the requirement in terms of achieving the output, the requirement in terms of achieving the quality. So you can see that the number of the machines as well as the complexity of the machines or the variety of the machines that are also very increasing. And that's why you can see that to maintain all those configurations of the machine, which are highly complex in nature, we can see that new techniques that are coming up. So early thinking in terms of maintenance was only a breakdown maintenance. That means whenever the machine will fail, whenever the machine will under breakdown only, during that only maintenance needs to be performed. Otherwise, whatever the state of the machine, it needs to be utilized. Because in earlier days, if you look at, there was not so competition. Most of it was a kind of a monopolistic situation where the products were unique, okay, and the products were not manufactured by many producers or many companies, so that there was very low competition. So whatever was available in the market, the customer has to buy those products. But in today's scenario, if you look at, there are multiple products that are available. So if one company is not performing or it's not delivering the product to the market, maybe based on a very wrong maintenance or ineffective maintenance strategies or practices. But of course, for a customer, the other products which are available in the market, the customer will definitely purchase those products. So the complexity of the machines are increasing, the complexity of the configurations of the machines are also increasing, and that's why new maintenance techniques are evolving. So we can see that nowadays we can see there are the preventive maintenance. In that preventive maintenance also we have a number of maintenance policies. We have a predictive maintenance, we have condition-based maintenance, or even the predictive maintenance strategies. So that's why, because of all these complexity, new maintenance techniques are being developed nowadays. Also, the awareness is increasing, because in earlier days, the failure was considered to be the unavailability of the machines only, okay? Because whenever the failure will occur, it has to be restored, it has to be rectified, and then the machine will be brought in operation so that again the production will continue. But nowadays, people are taking, or the maintenance is concerned in other dimensions also. For example, if the machine is failed, that means if it is not producing, that means you are losing the opportunity to produce. And if the product is not coming to the market, in that case, whatever the competitor's product that is available, the customer will purchase that particular product. So if the machine is not available, based on which you are not able to deliver the product to the market, the consequence is that you will lose the opportunity of earning based on the loss that you will incur of not selling the product. So this kind of awareness, or the awareness may be in terms of the other aspect, the safety aspect, or the environmental hazard that it may cause, all these awareness is increasing. And that's why you can see that nowadays maintenance is being given a very serious attention in the industries. And also, if we look at the maintenance and its connection with the other areas, for example, it may be related with the production, it may be related with inventory, it may be related with product quality. And of course, it will have several consequences related to the functioning of the other departments or sections in the industry are concerned. So that's why people are considering the role of maintenance, looking at these aspects that is related with production, related with inventory related with product quality. Because if machine is failed, and that means if you are not producing, and if the products are not produced, that means you will lose the opportunity. So maintenance will have an impact in terms of the inventory levels in the organization. It will have an impact in terms of your production schedule. Because if you look at the production scheduling and the maintenance connection, when we schedule the jobs, we look at the availability of the machine based on the availability of the freeness of the job, as we have seen in case of the last example that we have seen. But then in many situations, the availability of the machine is also very important, which is governed by the maintenance function. So nowadays, this awareness about the maintenance related to the other function is also increasing, and based on that, we can see that maintenance has to be given a thought from those particular point of view also. And also there is always a pressure to achieve high plant availability and to curtail the cost. Okay, because availability is one of the important factor related with the maintenance. So since the competition is very high, the markets are very competitive, we have to look at that how the machines will be available, so that based on that we can utilize the machines to carry out the production. Okay, so if you look at this is based on even certain research that equipment downtime reduction, it results almost 20.1%. The reduced material cost, it will get to 19.4%. The maintenance productivity improvement, it results to the tune of 28%. So this is based on the overall, we can say, research by one of these consulting firm. So that's why we can see that if we improve the maintenance, it will result in achievement of many performance or many productivity measures. So to achieve the improvement in terms of the maintenance performance, the industries, they need to have an optimal or the correct maintenance policy as far as the operations of that particular industry is concerned. Okay. So when it gets to the maintenance decision, the maintenance manager, there are several, we can say, questions that will come to the mind of a maintenance manager, that for a given machine, depending on the number of components in that particular machine, whether we should repair a machine or replace it with the new, or if it's a situation of a component level, then whether to repair the component or whether to replace it with a new, so that the machine will perform its operation. Should we carry out the preventive maintenance of the available resources as opposed to reacting to breakdown? So whether we should adopt the preventive maintenance policy, or we can continue with the kind of a breakdown maintenance policy or corrective maintenance policy only. And that depends on the kind of operations, because if you have a lot of orders to be processed, so that if we can utilize the machine, so in that particular situation, you may go for a kind of a preventive maintenance. Otherwise, there may be a possibility that there will be recurring failures or recurring breakdown. So again, depending on the operation level, depending on the orders that need to be processed, again, the manager has to think in terms of whether to do the preventive maintenance, and if it is a preventive maintenance, what should be the maintenance frequency, whether the maintenance has to be done on a weekly basis, whether the maintenance has to be done on a monthly basis, whether it's on after 15 days, whatever. Then at what frequency should the preventive maintenance be done? That is what we have discussed. And what is the cost of implication of the decision? Because you can see that if you do more maintenance, okay, what will happen? Your breakdowns will reduce, but then your maintenance cost will increase. Okay. So what should be the optimal frequency by which you will achieve the required availability of the machine, and at the same time, it should result in the lowest maintenance cost. So when it comes to a maintenance decision, that trade-off has to be achieved between the availability of the machines as well as the maintenance cost. Okay. Because if you are doing more maintenance to avoid the breakdown, your maintenance cost will increase. And at the same time, the availability of the machines will will improve, but then the machines will not be available for the production because the machines will always be in a shutdown state, or they will be under maintenance only. Okay, so that trade-off or that balance has to be achieved. Then can we assure a certain level of system availability? So based on the maintenance practice that you are adopting, whether it's a preventive maintenance, and in that preventive maintenance also, to what level it will result in the system availability, that is also one of the important concern for a maintenance manager. Then what are the factors that will influence the availability? And then based on the different approaches, you can see that result in better maintenance practices, maybe based on the Japanese philosophy, to what extent we can utilize those, and based on that, which maintenance practice or which maintenance policy we can adopt. So all these can become the important factors for a maintenance manager. So if we look at the maintenance performance, if we are concerned, the performance may be related with the equipment, it may be related with the maintenance task, or it may be related with the cost. For example, related to the equipment, it may result in terms of the availability that you can achieve based on the maintenance. So based on your maintenance practice, how much proportion of the time the machine is available. That means a breakdown free operation of that particular machine, which we call it in terms of the availability. Then the performance rate from that machine, and then to what extent it will result in the number of small or the big stoppages, when what can be the downtime for the particular machine. And of course, one performance measure that is popularly used is called the OEE, that is overall equipment effectiveness. So based on the maintenance, we can evaluate the performance, and of course, all these factors, those will be related with the equipment. Similarly, we may have the performance in terms of the maintenance task. That means what is the quality of the maintenance task, then how much is the change over time. That means when you are taking the machine for maintenance, in how much time you are repairing that machine, and based on that, in how much time you are again making it ready. Similarly, the planned maintenance task, the unplanned maintenance task, and the response time for the maintenance. So all these will be a part of the maintenance planning that needs to be taken into account, and that will form one of the performance parameter related with the planning of the maintenance. So this is nothing but this is related with planning of the maintenance task, which will result in a kind of a measure. And similarly, you may have the indicators in terms of the cost. That means how much is the maintenance cost that will get per unit, then what will be the production cost based per unit, maybe based on the maintenance that will be involved. Because if there are frequent breakdowns, of course, it will increase the maintenance cost, and then it will increase the production cost. And to have an effective maintenance, whatever the resources that you have utilized, whatever investment that is being done, then of course, what kind of return that you can get based on the investment that you have done it in terms of the maintenance resources. It may be in terms of the maintenance staff, it may be in terms of the equipment, the technology, or even the kind of a training that is being given to the maintenance staff. So all these will involve some kind of a performance measure in terms of the cost related to the maintenance program that you are following in the particular industry. Of course, there can be many performance measures related to the maintenance task. These are few which we have classified in terms of the equipment, in terms of the task itself, and in terms of the cost performance of the maintenance activity in the organization. Okay, so as we have seen that there are many maintenance factors. The routine type is an inspection wherein you can inspect the machine. Then if it is possible, you may do some kind of oiling, greasing, or lubrication in that as a part of the preventive maintenance. Then it may be a kind of a breakdown maintenance wherein whenever the machine will fail, only during that only the maintenance will be carried out. So the third category, it may be a preventive maintenance. So to avoid the breakdowns, you may have a kind of a preventive maintenance policy. And in that, even though the machine has not failed, you will do the inspection of the machine, and based on the requirement in terms of some oiling, greasing, lubrication, or if any small adjustment that need to be done, you may carry out that, or in some situation, depending on the requirement, you may replace the component, and based on that, you will make the machine ready so that it can achieve a required availability for its next operation period. It may be a kind of a predictive maintenance wherein some kind of a condition monitoring we can do. So we may look at few parameters, because whenever the machine it goes in a breakdown, or when the major failure it occurs, some signals or some symptoms it starts. Okay, so those signals or symptoms we can get maybe based on some kind of a monitoring that we call it as the condition monitoring or health monitoring of the machine. So it may be in terms of the temperature, it may be in terms of some kind of a vibration. So based on that, we may predict the condition of the machine, and based on that, we may carry out the maintenance. Or it may be in some kind of a situation wherein you can have an opportunistic maintenance. That means whenever there is an opportunity for maintenance, for example, the machine has failed, okay, and maybe the failure is based on certain aspect of the machine. But since now the machine is available for maintenance, and since the machine is now open, you may look at, apart from that particular fault, you may look at some other aspect of the machine, some other components, some other sub-assemblies in the machine, so that you are grabbing this opportunity to carry out the maintenance. So since the machine is dismantled, and now you are able to see the entire machine based on that particular fault, you can grab it as an opportunity, and you may do maintenance of the other components which are not failed. So you may do some kind of an adjustment, some kind of a repair, or maybe you can replace a small component, so that based on the state of that particular component, you may rectify that particular component. So in that sense, it's a kind of an opportunity that you are grabbing based on the failure of some other component. And since the machine is now dismantled, you can take this opportunity to do other maintenance of the components also. So there are many maintenance policies that may be adopted. And you can see that the cost of, if you look at the level of preventive maintenance that we discussed, that if the level of maintenance, preventive maintenance, with the level of preventive maintenance increasing, your cost of breakdown will reduce. Okay, so you can see that the cost of breakdown will reduce. And if you are looking at the preventive maintenance cost, as the level of preventive maintenance will increase, your preventive maintenance cost will also increase. So if you look at the total cost behavior will be like this. Okay, so you have to achieve some optimum level of maintenance between the breakdown maintenance and the preventive maintenance. Okay, so on one extreme, if you follow the breakdown maintenance, then you will see that your cost of operation will increase, your maintenance cost will increase. And on the other hand, if you are just following the preventive maintenance, because with the level of maintenance, your preventive maintenance cost will increase. So you have to keep a balance between these two. So you should have some policy in terms of, you should do some preventive maintenance, and then you may have the breakdown maintenance policy as well. Okay, so there are many maintenance policies that exist that will result in the optimal system reliability and safety. It will result in the performance of the machine, and it will be result in terms of the lowest maintenance cost. So as far as the maintenance theory is concerned, there are two kinds of maintenance policies. One, considering the single unit system, wherein the entire machine is considered as a single unit, and based on that, the maintenance policies has been implemented. And there is another system wherein it is considered as a multi-unit system, wherein we can have a situation of maintenance based on the, either it may be a group maintenance, wherein we are replacing the components in a group, so that we call it as a group replacement policy. So this may be a part of group replacement policy. So if the cost of the component is not high, but in that situation, if the consequence is very high, that means even if it's a small component that may be worth 100 rupees, but then the component is located at such an internal level of the machine that to dismantle the machine, it takes 10 hours. Okay. So in that particular situation, for those components which are not having a very high value, but then the consequence in terms of dismantling the machine or is very large. So in that particular situation, you may look at a group replacement policy. So whatever the components, you can identify those components and those can be replaced at a time. So even though that component has not failed, but as a part of policy, you will replace all those components. And in case of a single unit system, we may have a kind of policy. It may be a periodic time-based, it may be an age-based policy, it may be a failure limit policy, it may be a repair cost limit policy. So depending on these particular policies, we may adopt the different policies as a part of the preventive maintenance. For example, a periodic policy, which is very common in many industries. So whatever the machine or out of those machines, what we do, we will select a particular machine during during a certain operation period. For example, on a monthly basis, each machine by rotation will be considered for maintenance. So that's a kind of a periodic preventive maintenance policy. That means the machines are being taken for maintenance on a fixed interval. So the normal practice that you can see in industries is a kind of periodic maintenance policy wherein during certain week on a rotation basis, each machine is considered for maintenance. So that kind of policy is a preventive maintenance or the periodic maintenance policy. Another policy, it can be age dependent policy. That means after certain period of operation, okay, after certain period of operation, the machine will be taken for the maintenance. For example, let's say if it is 1000 hours of operation. So based on the 1000 hours of operation, so this 1000 hour will become now age of the machine. So such kind of policy may be adopted. And that means under this age dependent policy, whenever the component or the machine has reached certain age, at that particular age, the machine or the components, they are replaced, and based on that, the machine maintenance is carried. So this is kind of policy, and of course, a lot of analysis has to be done based on the age of the component, the operation level, and to decide with the policy. So age dependent policy.
Periodic policy is depend on duration or like hours of operation or like particular time period, whichever comes first or something like that. Like we are doing the service for vehicles, either the duration of 15 hours, this much hours this has worked, or this time duration, like in days, whichever comes first, like that.
So you can decide that what will be the age criteria. For example, let's say you have decided 1000 hours as the operational period. Okay. So that means the age of the component will change by 1000 hours. For example, let's say any new machine that you have started its operation. So the age of the machine is now 0 because it's starting, the component is new or the machine is new. That means it's starting with an age 0. And let's say now you have decided that after every 1000 hours of operation, so whenever the machine age will increase by 1000 hours, you will carry out the maintenance. So that kind of policy is a age-based policy, we call it. And in case of a periodic policy, after in every month, okay. So whether the machine has run for 100 hours or the machine has run for 200 hours, that we are not considering. So it's a time-based. So this policy, we call it as a time-based maintenance policy. And this is what is the age-based. So it may happen that depending on the requirement of the production, these 1000 hours may get completed after 1.5 months, or it may complete after 2 months. So in this case, the time will not be fixed. The age of the machine will be fixed. Okay, so it's a kind of a different policy. Or in some situation, it may be a failure limit policy. That means whenever the failure rate or the other reliability indexes that we are going to discuss. So whenever the failure rate will increase, so okay, so if we decide that if the failure rate is reached to whatever the predetermined level, so this particular policy will be based on the failure rate, and whenever any reliability index, that means that we are going to discuss, those we call it as MTTF or MTBF or any other measure. So if that particular level will be reached, we will have the maintenance. Okay, so that kind of policy is called the failure limit policy. That means once that particular failure level has reached, it will result in the preventive maintenance. Okay, or it may be a kind of a repair limit policy. So in this case, certain repair cost is estimated. Okay, because if the degradation of the machine is more, in that case your repair cost will increase. So this type of policy, we call it as a repair limit policy, so that whenever that particular the degradation of the machine has reached to that level, that means your repair cost is very high. So in that particular decided that either the machine will be preventively considered, or the component will be replaced. Okay, and this is a kind of a policy even we adopt it in many situations, that we take a decision that okay, if the repair cost is high, it is better to replace it with a new component. Okay, so if that particular repair limit has reached, in that case the decision is taken in terms of replacing it with a new one, so that you can replace the old component with a new component. So these are some of the policies that can be adopted. Of course, there are many maintenance policies. There is one more policy that we call it as a selective maintenance. So we'll take a break for 15 minutes and then we'll continue the session. Okay, we'll discuss about this policy after the break.
Okay, sir.
Okay, then. Yeah.
Okay, sir. Okay, sir. Okay.
Well, let's say one particular operation cycle of the machine is over, and based on that, let's say the machine is being available for maintenance during the preventive maintenance, or we can say that the machine is available maybe at some other maintenance opportunity. For example, if any major breakdown it occurs, and during that the machine is available. So this particular maintenance policy, it looks at the kind of, we call it as a subset of the maintenance. For example, there are n number of components in the machine. Okay, now when the machine is under maintenance, for a manager, for a maintenance manager, then the decision is that which component that needs to be given some kind of a repair, which component needs to be replaced, or which components we can skip the maintenance, because there are so many components that exist in the machine, but then the time that is available for the maintenance, or the resources that are available for the maintenance. For example, let's say the machine is available for maintenance and you have 12 hours of maintenance time, and in that 12 hours now, out of the number of components in the machine, the manager has to decide that which component has to be repaired, which component can be replaced. So that means this particular maintenance policy is in terms of the selective decision. That's why the name is selective maintenance here. So the selective word is in terms of, we call it as maintenance actions. And for a given component, there can be 3 maintenance actions. Either the component, it can be repaired, the component either it can be replaced with a new one, or for few components we can skip the maintenance. So the condition of the component is such that we will not do any maintenance and we will skip those components. So in that sense, this particular maintenance policy is called a selective maintenance policy. That means the decision is in terms of the selective action for the components. So this particular maintenance policy, we can see that it is applicable in many situations. For example, in case of the military equipments which are available after certain mission period is over, or in case of a production equipment where the mission period we can consider as the cycles between the preventive maintenance, or it may be doing any other maintenance or other major breakdown in that case. So this particular selective maintenance is in terms of the maintenance action, that means in terms of the repair, replacement, or we call it as skip the maintenance for a given component. And this is because the maintenance time during the mission break, we call it, is not sufficient so that all the components can be given some maintenance. So for example, in a machine, there are hundreds of components. So all 100 components cannot be maintained because the machine is available for a limited duration or for a limited time. So in that particular situation, it may be a kind of a selective maintenance which we can adopt, and based on that we may come up with the maintenance decision. And of course, it should, whatever actions that we have considered, whether it's a repair for the component, it's a replacement for the component, or for a few components for which we are not doing maintenance because the condition is such that it is good, so that we can skip maintenance and we can utilize the time for those components which are more degraded or which are having more, we can say, wear and tear may be related to the component. So, but of course, this decision of deciding this combination of repair, replace, or do nothing, it should result in certain performance measure. Either it should result in the required reliability of the machine, or it should be in terms of the required availability. Because for few equipments, reliability will be more important, and for few equipments, it will be the availability. Okay, so as it is mentioned that in case of a selective maintenance, we are looking at identifying the subset, and the subset is in terms of three actions that need to be considered for the component. Either the component can be repaired, either the component can be replaced with a new, or the component can be a do nothing. That means we are not doing anything for a component at this maintenance. It may be considered in the future maintenance. Okay. And of course, the analysis will be based on which component are repaired. So it will involve the replacement cost, which component are repaired, which will involve a repair cost. And even though we are carrying out the maintenance, there will be some future failures that may get associated. So of course, this entire analysis will be based on some of the optimization of these particular costs. We will not go into the details of the optimization, but as a part of the understanding, we can see that selective maintenance is concerned with these three particular maintenance actions related to the components. Okay, so this is what is a general, we can say, situation that you may find during any maintenance opportunity. So let's say this is what is the preventive maintenance at which you have been considered the machine, and before, based on that, you have certain last instance of the machine. Okay, and based on the last instance of the maintenance, this machine age, which is nothing but we call it as this last maintenance period. So let's say you have done a maintenance 1 month before, and after the 1 month of operation, the machine is available for the maintenance, that we call it as a current maintenance opportunity. And now at this particular maintenance, we have to decide. So there are n number of components you have. Okay, out of those components, you have to decide that which component will be repaired, which component will be replaced, and for which component we can say skip, or we call it as do nothing. So that the next operation period, that means let's say the machine will be in the next preventive maintenance, which may be after another 1 month. So you have to decide which actions need to be performed on the component, so that whatever is the production requirement in terms of the availability of the machine, that should get fulfilled in the next operation cycle. So of course, this analysis will be based on the optimization of the different costs that we have considered, and then depending on the different age of the components, we have to come up with this decision that whether the component can be repaired, whether it will be replaced, or whether it will be a skip or do nothing for a given component. So of course there is, this is a kind of policy that we call it as a selective maintenance policy. Okay, so this analysis we will not do it now. Okay. So is there any doubt related to any kind of a maintenance policy that we discussed? Okay, so okay, so we talked about the role of maintenance, and as we can see that the conventional way of thinking at maintenance is the responsibility of the maintenance. Yes, Mr. Neeraj.
Sir, what is the difference between inspection maintenance and selective maintenance? Because the activities we are doing in selective maintenance is the same we will do in inspection maintenance. We have to repair, or we have to replace, or we can keep the same thing.
See, inspection, when you say, you are just inspecting, okay, and maybe based on that you are doing some kind of an adjustment. So inspection will not say any kind of a maintenance.
But sir, in inspection we can judge the it is NG or OK component. We have to judge something in inspection maintenance.
See, inspection is a kind of activity wherein you can decide that whether we need the maintenance or not. Okay, and based on the results of your inspection, then you may have a decision in terms of deciding which component. But of course, that analysis has to be supported by certain, that decision has to be supported by certain analysis, because each component will have an age, each component will have its useful life remaining, each component will have the cost. So based on that, you have to decide. For example, based on the inspection only, you cannot take a decision that I will replace this component. So inspection is a kind of just an observation of the machine.
Okay, thank you, sir.
So based on the inspection, then you will have a decision that whether you will do the maintenance and what kind of maintenance you will do it. So for example, if you have done the inspection and then based on that, you see that there are many components which are broken. So many, let's say many washers or many seals or many other component, if there is a leakage inside, so you feel that, okay, this is not possible. Maybe in half an hour, we need to take this machine and we need to do preventive maintenance for many of the components. So then in that case, you will have to carry out the maintenance in terms of lubrication, in terms of fixing those whatever failure that you have observed in inspection. If any leakage is there, you have to take that kind of if any seals are broken, you have to replace those seals. So that will be a part of maintenance then.
Yes.
So inspection, we call it as a routine inspection. So for example, before starting the shift, let's have an inspection of the machine.
Yes,
so
sir.
it may result in some kind of a cleaning or some kind of a minor lubrication or anything, that we call it as an inspection.
Or the patrolling kind of thing can do on the line.
Yes, yes. Yeah. Yes, yes. So it's just an inspection. It will not involve the maintenance. When we are looking at maintenance, that means it will be based on certain action that we are going to implement for the given machine or for a given component. And of course, when we say it's a selective maintenance where we are looking at repairing, replacement, it will be based on the analysis of that entire age of the component, because component will have a cost. Okay, so just by inspection, we cannot analyze it. So we'll have to analyze in terms of what is the age, what is the reliability of it, and maybe based on that, you will come up with the decision.
Okay, thank you, sir.
Okay, because if you, it should not happen that you have replaced the component which can give almost 1,000 or 2,000 hours of life. But if you have replaced it preventively, you are what you can say, losing its useful life, isn't it? Okay, so one aspect that we have seen that maintenance has a connection with the other operations which are involved. For example, here you can see that the three major operations that we call it as the scheduling and the quality control, because the maintenance has a connection with the scheduling, maintenance has a connection with the quality. So if we just look at the maintenance, we see that the machine may fail due to the continuous running of the machine. Okay. And there will be a requirement in terms of preventive maintenance and the corrective maintenance. And whenever there is a preventive maintenance or a corrective maintenance, there will be a downtime. That means the machine will not be available for production. And we call it as the loss of production window. But if we consider the scheduling is based on an assumption that the machines are available. Okay, so when the schedules are planned, we don't look at, or the scheduler will not look at what is the maintenance requirement of the machine. And from the production point of view, or from the production department point of view, there is always a requirement that they need or they want machines to keep running. Okay, so and in many situations you will see that there is always a kind of a conflicting situation. Okay, that maintenance will say that machines are not being given for the maintenance. Production will always blame that, okay, the machines are failing. Okay, we are not able to complete the target. We are not able to meet the deadline. So there is always, you can see that a fight or the conflict occurs between the maintenance and production. And you can see that maintenance has a connection with the production. That's why in one of the slides, we have seen that now this awareness is increasing, that maintenance and production and quality, they have a linkage, and all these should come in terms of the coordination. But if you look at the conventional practice, we have a different department like maintenance department, production department, quality control department, and all these departments, they plan for their activities based on what performance they want to give. For example, production department will try to complete its target, will try to complete its deadline. Maintenance will try to look at how we can improve the availability, how we can reduce the number of machines that are failed in a certain duration of time. So they will always try to keep more maintenance related to the machine. So you can see that this kind of connection that exists. And similarly, if you consider the quality, if maintenance is being not done, or if maintenance is delayed, or if maintenance is not effectively performed, so if any component in that machine which has some effect on the quality, for example, if any belt is loose, and if that looseness of the belt is getting translated in some kind of the product that is manufactured on the machine, that means the quality will affect based on, let's say the root cause is that some component is not performing properly, or some failure has occurred, and based on that failure, even though the machine is running, but then it is having some effect on the quality of the product. So this reason is that maintenance is not being performed. The maintenance may blame in that case, okay, that productions are not giving maintenance machines, so we are not able to do the maintenance. Okay, and that's why we are not able to complete the maintenance, and from that point of view, the components are failing, and maybe because of that, the quality is affecting. And if quality is affected, it will result in more defective product, it will result in increasing the wastage, rework, and your scrap will increase, whatever, depending on the product that is manufactured. So you can see that in manufacturing scenario, all these three functions, they have a connectivity. Similarly, if we look at the inventory levels also, so if machines are not available, if production is not carried out, your inventory levels will also get affected. So that's why we can see that there is a kind of a connection between all the functions, and there is a need, there is awareness that this connection has to be considered, and there has to be a coordination between all the functions during the operations that needs to be planned. Okay, so that's why you will see that nowadays there are many combined or integrated approaches that are coming up, and based on that, the operations planning is being performed. But if you look at the conventional practice, all these functions, they operate with their own performance measure. Okay, so that's why there is always a conflicting situation, and to avoid that conflicting situation, there has to be a coordination between the different functions. And especially if we are looking at these three functions, for example, the maintenance, production, quality, there has to be a coordination. Otherwise, what will happen that the conflicts will increase, or at the industry level or at the management perspective, the performance of the overall operation will reduce and it may affecting the business. Okay. Okay, so this was about the importance of the and different policies related to the maintenance. We'll now look at one of the important aspect that is related with the machine maintenance is the reliability aspect. Okay, because the decision on maintenance and the decision on the other operational factors are many times related with the maintenance of the machine, and that too related with the reliability aspect of the machine. Can you mute yourself, Mr. Balasubramaniam? Okay, so we can see that reliability theory has a connection with the optimal maintenance plan, because as we have discussed, that when we have a decision in terms of the maintenance decision, maintenance action, of course we have to look at the reliability, because the availability, the reliability is based on what maintenance we are carrying out. Okay, and of course one of the important aspect of the reliability is the optimal maintenance plan. So whatever maintenance plan that we want to come up, it's based on the reliability. Similarly, the failure predictions, that means if you want to predict the failure, that what can be based on the current state of the machine, we can decide or we can estimate what can be the failure. So that is also based on, or that is also possible with the reliability. Reliability theory may be in terms of utilized for the mission reliability. That means if we want to perform the certain mission, what can be the reliability so that the required mission, it can be performed successfully. Similarly, it will result in the optimal spare parts, because based on the maintenance need in future, you will have to look at that what kind of spares that will be required. So reliability theory is also connected with the optimal spare parts or inventory that is required. It will also result in the warranty cost prediction. Okay, because based on the reliability theory, you can predict what can be the future failures, and based on that future failures, what can be the cost that may be incurred based on the warranty that is being given for a product, and maybe based on that we can predict what can be the warranty cost associated with the product. So similarly, when the companies, they come up with the warranty policy, that means the 1 year warranty, 2 years policy, of course that policy is based on what kind of reliability that will exist for the particular product or for the particular machine. And based on that, the warranties are being given, and based on that, the warranty costs can be predicted. Similarly, we can utilize it in terms of what will be the life cycle costing. Okay, so as a part of the life cycle costing, when we look at the cost right from the acquisition of that particular machine, so that means when the machine will start its operation till it will end its operation, that means when the machine will be scrapped. So that particular life cycle costing will also involve to some extent the maintenance theory, and to that extent it will involve the reliability theory. So reliability theory or reliability has so many aspects associated with the functioning or operations of the machines. And from that point of view, we will see now that what do you mean by reliability and what are the different aspects of the reliability measure. So in general, when we say reliability, so its reliability is nothing but it's the chance, or we call it as the probability. So reliability is nothing but it's the chance or the probability. So the ability of the product to perform as expected over a time. Okay, that means if we have purchased, let's say, some electric bulb or maybe some tube light, so we are expecting that it should give the light, it should have sufficient life. Okay, and that is nothing but what? So these parameters, when we say or when we analyze, it's nothing but the reliability that we are expecting out of that particular product. So when we say reliability, it's the ability of the product to perform as expected over a period of time. So when you have purchased some, let's say 40-watt tube light, so you have certain expectation in mind to have a illumination. Okay, if that particular illumination is not achieved, if it is giving a dim light, then you will say that the product is not a reliable product because you are not getting the expected performance. Okay, if you have purchased that tube light and if after 2 days it has failed, that means after 2 days it has fused. So in that particular situation, again, you say that the reliability of the product is not good because you were expecting that at least the tube light should function maybe for 6 months or year. But if within 2 days or 3 days, if it is fused, so in that case, you will say that the reliability is not the proper, or it has a low reliability. So reliability is nothing but it's the probability that a product, that is a piece of equipment or a system, perform its intended function. So whatever is the intended function that you are expecting out of the product or the system for a stated period of life. Okay, for example, when you have purchased a mobile phone, you are expecting that it should perform at least for 1 year, for 2 years. If within 2 days, if it has failed, if it is not connecting your call, that means it's not a reliable product. So whenever we say reliability, it's the probability of the intended function for a stated period of life under the specified operating conditions. Okay, so that means there are 3 important aspects related with reliability. One is the intended function, the second one is the stated period of time, and the third one is the specified operating conditions. Okay, and based on that, when the product is performing, we consider whatever the probability of performance, we call it as a reliability. That means it's a chance or it's a probability. Okay, so reliability, if we compare it with the quality and reliability, okay, so what do you mean by quality? When we say quality, so when you are expecting or when you say the quality of a product, that means you are considering that whatever is the performance of that particular product when the product is manufactured, that means at t equal to 0. Okay, and when we say reliability, reliability is the performance to the specification at time t greater than 0. That means what? Let's say you have purchased a new mobile phone. Okay, so how we will say, or how we will define its quality? So whatever is the performance that is being designed and manufactured in the product, and based on that, when the product has come out of the factory, that means the product is available in the market. So whatever the performance when it is a new product, okay, that will decide its quality. But over a period of time, whatever the performance that the product will give based on its specification, that we call it as a reliability. So quality is the, we can say, quality is the reliability at time t equal to 0, and reliability is the quality at time t greater than 0. So let's say after 6 months, whatever the quality of that particular mobile phone, you can say that it is the reliability of that particular product. So in that sense, quality and reliability, we can say that quality is the reliability at time t equal to 0 and reliability is the quality at time t greater than 0. That means over a period of time, if the product is performing as per its intended function, as per the specified period of time in the specified condition, then you say that it's the reliability of that particular product. So when we say reliability, we have to focus on these important factors, that reliability is the probability. Okay. Then the product is required to give the adequate performance. So that is one of the element of the reliability. The second is the duration of the adequate performance is specified. Okay. For depending on the product, its intended function and over a specified time that will be specified. And if that particular product is performing within that specified period, then we say that the reliability we are achieved. And of course, will be an environmental or operating condition. So in which operating condition we are expecting the performance of that particular product. For example, if we have purchased an air conditioner, okay, and if you are using it in a very extreme hot condition, or if you are using it in a moderate hot condition, okay. So of course, in that particular environment, the performance of the same brand of maybe the air conditioner will be different. So of course, we have to look at the environmental condition also. So if we want to say about the reliability of that particular product or that particular AC, we have to look at that in which environmental or operating condition it is giving the performance. You cannot compare the performance of an air conditioner if you are using it maybe in Delhi or maybe in some other situation where it's a very hot climate, and if you are using it maybe in some kind of a moderate or a pleasant environment like in Bangalore. So you cannot compare the performance or reliability of the same AC based on its operation in Bangalore and based on its operation in Delhi. So from that point of view, the environmental or operating condition is an important aspect of the reliability measure. Okay, so when we say failure, so failure is nothing but it's the lack of ability of a component, equipment or subsystem to perform its intended function at the required performance level. Okay, for example, the engine valve would indicate the primary failure mode as incomplete closure of the valve. Okay, so that's a kind of failure and it may result in leakage around that particular seat so that it will not give the proper function. So in that way, we have to decide that what can be the failure of the particular component, and based on that, we can define the failure. Now, if we look at the system reliability, whenever any system, the system is always a combination of the individual components. And when we look at the reliability, the reliability of the entire system will be based on the individual reliabilities of the component or subcomponent or subsystem that are in the system. Okay. So when we look at the entire or the reliability of the entire system, it is the reliability of the individual components that will get involved, and based on that only, we will get the overall system reliability or overall system performance. So the arrangement of the components or the systems may be either in series, for example, this kind of a situation wherein you have a number of components which are connected, and failure of any of the component will result in failure of the entire system. For example, let's say if this is the system that we are considering. So let's say it's an arrangement of the engine, transmission, then some kind of a differential, and there are so many systems. So even if any of the system fails in this particular arrangement, the entire system will fail. So this type of system, we call it as the series system. So the reliability of the individual component will be very important to decide the reliability of the entire system in this case. Okay, so in this case, the system reliability that we call it will be based on the individual reliability. For example, the reliability of this system is R1, R2, R3, and so on. So it will be R1 multiplied by R2 multiplied by R3 and so on. So this is what is the kind of a system when we say reliability of the series arrangement. Similarly, we may have a kind of a parallel system wherein unless all the components or all the systems in this particular system fail, the system will not completely fail. So as compared to the series system wherein any of the system it fails, it will result in the failure of the entire system. And in this particular arrangement, unless all the subsystems that are existing in this system, they fail, the system will not fail. And in this particular situation, the reliability of the entire system is nothing but is equal to, we can say it is 1 minus the unreliabilities. So U here is, we can say, unreliability. And this we can find using 1 minus R1, 1 minus R2, 1 minus R3, so on and so forth. Okay. So there are many systems in which we need to have the redundancy, we call it, or it's a kind of a parallel arrangement. For example, in case of an aircraft, we have two engines. Okay. So there are two systems that are existing in an aircraft, and based on the reliability of the individual systems, the entire aircraft or aeroplane will work. Okay. Because if it's a kind of a series arrangement, in that case, if any of the component or if any of the system it fails, it will result in the entire failure of the system. So in case of an aeroplane or in case of other system where a very high reliability is expected, in that particular situation, we should have a kind of redundant pathways or redundant systems, and that say we should have a parallel kind of a system. So this is what is about the series or the parallel arrangement. Even in our human body also, we can see that there are many systems which are in series, and we have some kind of redundancy or the parallel arrangement that is available. For example, if you look at the connection between the lungs and the heart, these are a kind of a series system. But if you look at the kidneys, we have two kidneys. So even if one kidney is performing, the system will not fail. The human body will function. So in that way, unless all the subsystems will fail, the system will not fail, or the reliability will not be impacted in that case. Okay. So we'll take few examples that how we can estimate these.
How to predict the reliability of individual component, like the weighted distribution, that kind of thing?
Yes.
How is there any example on that one?
Yes. I'll come to that. Okay. So Okay, so before taking the example, we will understand what do you mean by failure rate and how do we estimate the reliability based on the different function. So failure rate, or we denote it with a notation lambda. So failure rate is nothing but it is the rate at which the product fails. Okay, so that we call it as a kind of a failure rate. That means the rate at which the product fails. And there are two other indices we can say by which we can measure or we can evaluate the reliability, that we call it as MTTF. That is nothing but mean time to failure. And there is one more measure that we call it as MTBF, which is mean time between failure. Okay, so MTTF, it relates to a repairable. Yes. Any doubt here? So this is applicable to a non-repairable system. And this particular is applicable to a repairable system. Okay. So for example, in case of the electronic components, or maybe let's say an electric bulb, we can have an MTTF, that is mean time to failure. Okay. So this MTTF, it applies to a non-repairable system which cannot be repaired, whereas MTBF, that is mean time between failure, is applicable to the systems which are repairable. That means the equipment or the system will start its functioning. There will be some failure that will occur. Okay, that failure will be repaired. Again, the machine will start its function, and based on that functioning is again the failure will occur. So this particular time period, that we call it as the mean time between the failure for that particular product. So failure rate, when we say the failure rate is nothing but it's the number of failures over the operating period. Okay, so this we normally define as failure per hour, or whatever the period that we want to mention here. So for example, let's see that how we can find the failure rate or the MTBF. So MTTF and MTBF, we can identify or estimate based on the failure rate. So it is nothing but MTTF or MTBF is nothing but it is 1 by lambda. That is 1 by failure rate will give you the MTTF or the MTBF. So MTTF is applies to the non-repairable system, and MTBF it applies to the repairable system. So it is nothing but operating period or operating time based on number of failures. Okay, so we'll take one example, and maybe based on that we will see that how we can calculate the MTBF or the failure rate. So let's say there are 20 units. So 20 units have been tested, and then based on that, 20 units have been tested for 1000 hours. Okay, and based on that, there are 6 units which have failed. Okay, and let's say the failure time of these particular, so first has failed after 550 hours, second has failed after, let's say, 680 hours, third has failed after 790 hours, fourth So one has failed after 480 hours, let's say 790, 860 and 620. So these are the failure instances out of these 20 units. And now if you want to establish the failure rate, so what will be the failure rate for this particular system? So the failure rate we can calculate using number of failures divided by the operating time. Okay. So how many number of failures here? There are 6 units which have been failed. And what is the operating time? So the operating time will be the summation of all this time. For example, 480 plus 550 plus 680 plus 790 plus 860 plus let's say here 620. So this is the operating time for the 6 component, plus there were 14 components or 14 units which have completed its 1000 hour of operation. So that will be equal to 4 into 1000. So whatever this value will come, it will result in the failure rate for that particular product. Can you estimate this value quickly if you can? Can anyone estimate this value?
0.0003.
0.00033. Okay. So 0.0033, it will be the failures per hour. Okay, but then many times we are concerned with when we go for let's say we are purchasing any equipment or purchasing any product, and if the manufacturer, if it specifies that the failure rate is 0.00033 per hour, that reliability measure is not so effective in terms of our understanding, or it not in terms of establishing the performance. So in that case, we may be consider it in terms of either the MTBF or the MTTF. So depending on what type of component it is, it may apply either it's a MTBF or MTTF. So in that case, if you say that 1 by lambda, so if you just take the, how much it gets?
2996.66.
2996. Okay. So now this makes a sense that when we say that if the mean time between failure for the product is 2996 hours, in that case we can expect the performance or the reliability of the product, that okay, at least for if once the product is restored, its mean time between failure, that means it will perform its function for at least 2996. Or if it is a kind of a non-repairable product, that means whenever the product will function, or if I purchase this product, at least it will function for 3000 hours of operation. So in that way, it's a kind of the reliability index that we can get based on this particular performance measure. That is either it may be in terms of the MTTF or MTBF, depending on whether the product is or the component is repairable or it's a non-repairable kind of system.
So this reliability is for individual component or for system as a system? This reliability calculation is for an individual component or as a assembly level, system level? Whatever you have calculated.
You may do it maybe at the system level, maybe at the machine level, or you may do it even at the component level. So depending on how you are considering the configuration. So for example, if you are looking at the failure of the particular component, and based on that, if you want to evaluate the reliability, you may evaluate the reliability at that particular level also. So you can have the reliability measure at the component level, at the subsystem level, or even at the entire system level also.
But we are talking about the multiplication of all these reliabilities for serious system, parallel system. So how that can be achieved? Like if this is
so you may have the reliability in terms of at the component level, and let's say if you have let's say you have a flow shop kind of a manufacturing where you have a number of machines, okay, and all those machines will feed the part from one machine to next machine. That means the earlier machine will feed the part to the next machine. So in that case, depending on the reliability of the individual machine, if any of the machine will fail, your entire line will fail. Okay, so in that case, it's a kind of a series system that you can consider or you can model, and based on the individual reliability of the machine, you can expect the reliability of the entire system.
Then in that case, we need to multiply like lambda1 into lambda2. Like in that way, we need to multiply.
No, lambda is not the reliability. Okay, using this, how we can estimate the reliability, that we will see it.
Okay.
It's a failure rate. Failure rate is not the reliability.
Okay.
Okay, so depending on what kind of distribution it follows, you have to consider its reliability.
Okay.
Okay.
I have one doubt.
Yes.
Sir, let's take this example and let us consider that there are 20 electric bulbs. Each bulb is running for 1000 hours, right? And some bulbs failed at the hours, like you have already mentioned. So how does this data, that 2996 hours, make sense to me? Because each bulb will maximum run for 1000 hours.
So reliability is a chance. It's a chance. Okay, it's a probability. So probability, when you say that, let's say based on this, you can say that the mean time between failure for that particular product. So it's a testing that you have done. So of course, you will have to do, depending on the product, you will have to create use certain sample, and based on the sample testing and based on the result, you may have an estimation of the mean time between failure here or the mean time to failure, whatever, depending on what kind of system it is or what kind of product it is, repairable or non-repairable, and accordingly this particular factor will apply to that. Okay, and now based on this, we may have an estimation in terms of the reliability, and based on that, then you can say that this particular product is having a reliability to that level, so that if we are purchasing this product will have a kind of mean time between failure. That means it will give a failure-free operation for at least whatever this value, 3000 hours, or in this case, it is 2996 hours.
Okay,
so it's a probability, it's a chance.
Yeah, but if
so based
I
on this estimate,
only one electric bulb, then how can I know the probability? Should I divide it by 20 further? If I purchase a single electric bulb only. Rather than 20 units, I'm only having one electric bulb. So how can I know the reliability now from this MTBF or MTTF?
See, unless you have a sufficient sample, okay, you cannot have the estimates based on just testing of one bulb only.
No, but let us say that company is providing me that this bulb is having the reliability of 2996 hours, and then I go to purchase that bulb.
See, 2996 is not the 2996 is not the reliability. Okay, it's one of the index to evaluate the reliability of the product. 2996 is not the reliability. Reliability is a probability that we will see how we can evaluate it. Okay, so if the company has given you the probability, in that case, we can say that whatever this probability or reliability that is obtained, it is based on this type of analysis, and based on that, we can be assured that, okay, if we are purchasing this product, the product will have a kind of mean time between failure of 2996 hours.
But sir,
So that will
probability
indicate the
is
reliability that you
unitless,
can
right?
extract for that particular product.
Probability is always unitless. It is always in fractions. So like 2996 is, I don't get like how does it?
2996 is not the probability, it's not the reliability. Okay, 2996 is what? Based on this particular kind of a testing, based on that, this is what is the failure rate of that particular product which is manufactured. Let's say these 20 bulbs have been manufactured and a kind of testing is being done on that. Okay, and based on this testing of these 20 bulbs, we have come up with a failure rate. If you increase the sample size, the failure rate may differ. But on an average, you will have certain failure rate. And based on that failure rate, you may have the MTBF or MTTF in that case. And based on that, then you can identify or calculate the reliability. Okay, we'll discuss it, and based on that, if you have further doubt, then you can ask. Okay, so let us first finish this, and then maybe based on that you can.
Sir, one question. Sir.
Yes.
Sir, and you talk about MTBF or MTTF. So that means both are same, sir? What?
Yes, mean time to failure is applicable to a non-repairable system. Okay, so whenever you have purchased any, let's say, electric bulb, and if whenever it will fail, it cannot be repaired. So you call it as mean time to failure, mean time till failure. So how much life it will give, or a useful life you can say, till its failure will occur. But for a repairable system which you can repair, the performance we can expect in terms of how frequently it will fail.
So
that means it is in terms of, it is mean time between failure, we call it.
Understood, sir. So for a MTTF, you mean to say that MTTR is 0?
MTTR is?
0, because we are just replacing. We are not doing any repairing. So MTTF case, no.
There is no MTTR applicable.
Applicable, okay. It is not
no
applicable.
MTTR applicable. Yes, yes. It's a non-repairable. It's always to be replaced with a new.
Yeah. Like
okay,
in
for
quality
example, bulb you cannot repair.
Yes, sir. Like in quality, the destructive testing, it is just throw away. That's all. We cannot replace.
Yes, yes.
Okay, sir. Thank you.
Okay. Okay, so depending on what kind of distribution it follows, the reliability is expressed in terms of R equal to e to the power minus lambda of t in case of exponential distribution. And the reliability is given in terms of, so this we can express it as e to the power okay, so this is the way we can evaluate the reliability. So we can write it as, for an exponential distribution, RT is equal to e raised to power minus t by eta. Okay, so before that, we will see the expected life cycle or the equipment life cycle, which is given by this type of curve. So any product, it will follow the kind of curve over its life cycle that is being reflected by this type of pattern. And because of this particular shape, this type of curve is called the bathtub curve. Okay. So if we look at the failure rate versus the operating time of any product, So you will see that during the initial phase, there will be more failures that will occur. That means during initial phase, the failure rate will be high. When the product is conceptualized, when the product is designed, and those type of failure, we call it as early failure period, because during the early phase of the product development, because of maybe some design flaws, or maybe because of the flaws in the raw material, because of the flaw in the process, there will be a lot of failures. And over a period of time, based on the rectification of those flaws, maybe related with the process, maybe related with the product, maybe related with the design, or whatever the other reason, the failure rate will start decreasing. Okay, so it will result up to this point, at which the failures, or whatever the early failures that we call, maybe based on some design flaws or process or maybe material, all those will be rectified. And then from this particular point till it reaches this particular point, it will have a kind of useful life, because in this period, whatever the early flaws or defects that were existing in that particular product, all will be rectified. And then you will see that from this phase to this phase, the failure rate will almost become constant. The failure rate will become constant, and in this particular zone, we consider it as a constant failure rate. And this is governed by a kind of exponential distribution. So the probability distribution that will fit to the failures in this particular zone will be the exponential distribution. So you can see that whatever the failure rate that will come during this, because during earlier phase, whatever failures that were existing, those were because of any of the flaw, which based on the we can say testing and design modification or process modification, those are rectified and the failure rate will decrease. So this we call it as a decreasing failure rate period, DFR. And over a period of time, all the failures will be rectified, and you will reach to a certain state during which the failure rate will become constant. Okay, and constant in the sense the failure will be by chance. Okay, and that particular phase we consider it as a useful life period. And after certain duration, after certain period, then the failure rate will again start increasing. With this we call it as the increasing failure rate. And in this particular phase, the failure may be because of wear and tear, or because of age of that particular product. So after the certain age of the machine or age of the product has been attained, you will see that again the failure rate will start increasing. And for increasing failure rate, then we consider another type of distribution that we call it as, or the failure in this particular zone will follow the Weibull distribution. Okay, and this Weibull distribution is characterized by two parameters. One we call it as a beta, and the second one is called eta. So this beta is called the shape parameter of the distribution, and this eta is called the scale parameter. Okay, so based on this typical zone where the product it lies, so mostly we are concerned with the useful period of the useful life period of the product, in which the failures will follow the exponential distribution, or we are concerned with the wear out period, during which the failures will follow the Weibull distribution. And in that case, the distribution will have these two parameters. That is, one we call it as a beta, and second one we call it as the eta, or in some text you will find it denoted by even theta also. So either eta or theta, but it represents the scale parameter. Of course, we will not go much into the details, because we will see that based on the kind of distribution the failures follow, how to estimate the reliability of the particular product or the reliability of the component. Okay, So if it's a kind of an exponential distribution, the reliability is given, R of t is given as e raised to power minus lambda t, where lambda is the failure rate. So which you can say it is e raised to power minus t by theta if you are denoting scale parameter with theta. And for a Weibull distribution, it is given by e raised to power minus of p by eta to the power beta. So where beta, it indicates the shape parameter. So just to give an idea that how this Weibull distribution will work. So the shape of this will be the beta, and whatever the spread that it exists, it will be given by the eta, that is scale factor. So this is shape parameter. So depending on the value of beta, whether it's 1, 2, 3, your distribution will have a different shape. Okay. And when beta is having a value greater than 3.5, the Weibull distribution, it gets to a normal distribution. Okay. And in that case, then we can apply all the statistics that is related with the normal distribution. So of course, we'll not go much into the details of it. We'll just consider here that how do we estimate the reliability based on the MTBF or MTTF, and in which zone it is lying, whether it is exponential, because if it is a useful life period, in that case, the distribution will be of kind of exponential distribution. And if it is in the wear out phase, when the component has or the product has reached certain age, in that particular situation, it will start following the Weibull distribution, where the failure rate will increase. Okay. Okay, so we'll see how do we estimate it. Okay, so let's take this example, wherein the same example we have considered of 20 units, and now we want to identify or we want to establish the reliability. Okay, so let's say we consider the exponential distribution. That means which phase we are considering? We are considering the useful period. Okay. So we are considering the reliability in this particular zone. So for this, the reliability at time t will be given by e raised to power minus lambda t, or this is also equal to e raised to power minus t by theta, and theta here is nothing but MTBF or MTTF. Okay. So now in this case, let's say MTTF is equal to 2996, since we have considered the example of the electric bulb. So now in this case, let's say we are interested that what will be the reliability. So MTTF is how much? It is 2996. So if we are concerned with what is the reliability at 1500 hours, because reliability is always expressed at a particular time. So let's say we are interested in reliability at 1500 hours. So in that case, reliability will be equal to e raised to power minus t by theta. So minus 1500, and theta is nothing but it's an MTTF. So this is 2996. So this will be equal to
0.6095.
So you can use Excel, and in that also you can find using an exponential function how much it gets.
0.6095.
0.6095. So this is what is the reliability. That means if you are considering to purchase this product, you can expect that by 1500 hours, it will give the reliability of 0.60. So the probability of functioning this particular product will be 60%. Or in other way, you can say that if 1000 products have been used or 1000 products will be tested, 60.95% of those particular products will perform the intended function at 1500 hours. So if you change the time, your reliability will change. For example, if you make it at 2000, if you make it at 2500, your reliability will differ. So what you can expect at 2000 hours, whether it will be more or less?
It should be less.
Okay, because MTTF is how much? It is 2996. So as you approach toward MTTF, your reliability will decrease. Bhushan, now is your question answered?
Yes, sir.
Now are you able to relate the MTTF and the reliability?
Yes, sir.
Sir, one question. Whenever
So now you can expect that whatever bulb now you have purchased, okay, you can expect that at 1500, you can expect the chance of functioning is 60%. So the interpretation of this probability or reliability is that if 1000 bulbs you will use, at least 600 out of those will perform the function up to 1500 hours.
Sir, one question. Whenever we purchase a fridge or washing machine from home appliances, they will give the warranty life in 1 year or some months duration. So the meaning is like 100% you will pass that 1 month, 1 year or that duration, or what is the meaning for that one? The warranty. So 100% of the 100% it will pass. Like probability is 100% it will work without any failure for the duration or.
Okay, you mean to say when the company they give a warranty of let's say 1 year. Okay, so that means what? It's a failure-free operation that the company is considering for the product. It will giving you an assurance that based on whatever reliability that is built into the product, okay, they are expecting that at least for 1 year there will be no failure. But then of course it's a reliability, it's a chance. So it may fail or it may, and in that case, if it is failing, they will take the ownership of those failures, and based on that, so for a company, they are considering it to give you a better reliability in terms of the product, maybe of the order of 0.99.
So they are confident if they are producing 100 numbers, all the 100 numbers will go through the time period without fail. That is their confidence level, correct?
No, can you repeat it?
So if the company is producing some 100 numbers of home appliances, so they are confident that all the 100 numbers will pass that duration, 1 year or something, the warranty duration, without any failure. That is their confidence level.
See, there can be a different context to this particular point that you are trying to consider, because depending on the operational costs, the profits, and other factors that are involved. So let's say for a company, to the customer, they will assure that the reliability is 100%. Okay, but from their operational point of view, they have to achieve some kind of a trade-off in terms of the warranty cost that they have to give. Okay, and of course that will be based on the entire reliability analysis, the kind of reliability that will get involved or that they have designed into the product, and based on that they will come up with the warranty. So this warranty optimization is again based on the reliability theory. So based on what kind of design, what kind of other features that are involved, the company, they will try to evaluate the reliability, and based on the reliability estimates, the warranty decision will come. And that means whether to give the warranty for 1 year, 2 years, 5 years, it depends on what kind of reliability that is built into that particular product. Because when the company is giving you the warranty, they will have to also look into account the warranty cost, because for company also it's a chance. For a customer, the company will give a kind of 100% reliability. It's an assurance. But the company has to come up with a trade-off that what is the chance, what is the survival chance of, let's say they are selling 100 units, and based on that, how many units will survive the 1 year period of warranty that they have considered. And based on that, if failure occurs, to what kind of cost that will get involved as a part of the warranty. So all that trade-off they will have to achieve. Okay. Yes. So this is based on the exponential distribution. Let's look at the reliability based on, let's say, a Weibull distribution. So let's say we have beta equal to 2. Let's say we have eta, that is, this is the shape parameter. This is the scale parameter. And let's say now we are interested in time t. So reliability at time t equal to will be given by e raised to power minus t by eta to the power beta. So using this particular expression, you can find out the reliability. So this will be e raised to power minus t. In this case, it is 10,000 to the power how much value it comes?
Zero 0.082.
0.082. Okay, so whatever. Okay, so what you can say that the reliability at this particular time of 10,000 will be of the order of 0.082. So depending on what kind of distribution it following, based on the bathtub curve that exists for the product, you can evaluate the reliability. Okay, and based on the system configuration now, you can do the reliability estimation, whether it's a series system or whether it's a parallel system. So for a series system, it will be the multiplication of the individual reliability. So you can see that, let's say if all these systems, let's say there are 3 systems and each system will have a reliability of 0.9. So this is 0.9, this is 0.9, and this is 0.9. So if you look at the overall reliability of the system, this will become 0.9 into 0.9 into 0.9. So this will get to almost how much? Around 0.72.
.729.
Okay, 0.729. So you can see that even though the individual reliability is very high in this case, for example, it was 0.99, a 0.9, but then the overall system reliability in this particular case, where the arrangement is a kind of a series arrangement, in that particular case, you can see that the system reliability gets to a very low value. So to improve the reliability, some kind of redundancy has to be built by using the parallel system. Okay. So in case of a parallel system, we can evaluate the reliability based on. So here you can see that there are 4 systems which are connected in parallel, and now the individual reliability is 0.9. So the system reliability in this case, it will be 1 minus R1 into 1 minus R2 into 1 minus R3 into 1 minus R4. Okay, so in this case, it will be 1 minus 0.1 into 0.1 into 0.1 into 0.1, and this will get to around 99.99% reliability. So in those equipments which we expect a higher reliability, for example, in case of the systems like aeroplanes or ships, we need to have some kind of a parallel system so that will ensure the very high reliability. But of course, when we look at a high reliability, it will always involve a cost. So we cannot have on a manufacturing line that there is a standby machine which is located so that if one machine fails, we can use that standby machine. Otherwise, in that particular case, to ensure the high reliability of the system, the cost will increase. Okay. So this is the way we evaluate the reliability in terms of a series or a parallel system. And for a combined system, you can evaluate it. So you can, I will mark this as a practice example. So you can see that this particular arrangement, you can represent it with one block of the system reliability for this. This will be a system reliability of this parallel arrangement. And then it will become a series system with this particular block. So what will be the reliability of this system? It will be 1 minus 0.5 into 1 minus 0.5 into 1 minus 0.5. So this will become the reliability of this particular block. Let's say A, let's say B here. So RA will be this one, and what will be this block? RB will be 1 minus 0.85 multiplied by 1 minus 0.85. So this will become, so the parallel system, first you will convert it as a part of series, and then you can establish the entire. So what will be the system reliability in this case then? It will be 0.85 multiplied by this RA, multiplied by RB, and multiplied by 0.95. So this is what is the analysis you can do it.
Sir,
So
I have
in
one
many
doubt.
systems, you will see that the system is a combination of series parallel system that will result in the entire the reliability of the machine.
Sir, I have one doubt. Sir, in like previous example, in equipment life cycle, while calculating exponential distribution, we know how to calculate lambda, but in wave pool distribution, we don't know how to calculate eta and beta. And when to decide like the cycle of the life cycle of equipment has crossed the useful life period, how do we decide that?
It is
Is
based
there
on
any parameter?
the correct. It is based on the distribution or entire analysis of the failure. Okay, so you'll have to do testing based on the failure data that you have. You can fit that particular distribution, and based on that, you will get to know to what particular distribution it fits to that. And based on the fitting of the distribution of the failure data, you may get these parameters. Okay, so if that particular it fits to a Weibull distribution, it will give you the parameter, the scale parameter, shape parameter. So entire Weibull analysis that
We
you will
can
have to
do this
perform
analysis only for the system which is like proven. We cannot do this analysis for upcoming system, like when we don't know like what are the results. So we cannot perform this analysis, right? It is only for the proven systems and the results when available with us.
To some extent, you can use the simulation approach also. Nowadays, there are so many simulation softwares that are available. So you can simulate the system, and based on that, you may find it out.
Okay.
So is there any doubt related to the estimation of the reliability in terms of the failure rate, and based on that, based on the systems, series system, parallel systems? So you can see that in many configuration, it will be a mix of the series parallel arrangement. So in many electronic equipments, in many other systems, it will be a combination of such kind of systems wherein it will be to ensure that particular reliability level, it has to be a combination of series parallel arrangement. But of course, that has to be supported with the cost. Okay. For example, aeroplane, it cannot work with only one engine. the reliability will become very less. So to ensure that high reliability, it has to be a kind of a parallel system has to be there. Okay, so we stop here our discussion for the today's session. If you have any doubt related to this, maybe you can quickly ask. Otherwise, based on the reading of the material, and if any doubt it arises, you may ask through email also. Okay, so we stop here for today. Okay, thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Yes, sir. Thank you.
Thank you very much.
Thank you, sir.
Thank you, sir.